Hi. Hi, hi, and welcome to Declutter the Mind for Focus. Let's start by finding a chair or comfortable spot to sit. Hi, and welcome to Declutter the Mind for Focus. Let's start by finding a chair or comfortable spot to sit. It can be a desk chair or a cushion on the floor, as long as you're able to sit with your back straight but comfortable. With your eyes open, begin by taking a few big, deep breaths. Breathing in through the nose and out through the mouth. On the next out breath, gently close your eyes. Begin to notice the physical points of contact. Start to feel your weight on the chair or cushion you're sitting on. Notice your legs touching the floor, your back against the chair. Notice your arms and hands in your lap. Bring your attention to these physical sensations. And now, notice a specific physical sensation. Maybe it's your back against the chair, and just focus on that sensation for the next few moments. And now, draw your focus in to the breath. Let's begin to train our focus by placing it on the simplest area, your breathing. Pay attention to each breath as it passes and the sensations of breathing. We're not forcing the breath here, just placing our focus on our natural breathing. Maybe you notice this more in your chest or stomach. Maybe it's your mouth or nose. Wherever you feel it most or find it easier to place your focus, leave your attention there. And you'll notice as we begin to do this, your mind will begin to wander. Part of training our focus here is to notice whenever the mind has become distracted and gently bring the focus back to the breath. And now start to count the breaths as they pass. The breath in, 1, the breath out, 2, until you reach 10. Once you reach a count of 10, start over and count the breaths again. If you've noticed the mind has wandered, gently return to the breath. Don't judge it, since judging is thinking as well. Just notice you've been distracted and start to count over. Continue to focus your attention on the breath. Let's begin to notice the stages of a complete breath. From the breath in to the very short pause that follows, to the breath out, and the very short pause before taking in another breath. Notice any stray thoughts, but don't dwell on them. Simply let the thoughts pass and gently bring the focus back to the breath. And now, in the final minute here, just release all focus. Allow your mind to do what it wants. And now, gently return the focus back to the body, back to the physical points of contact. And now, gently open your eyes and notice how you feel. You've just completed the meditation session. This practice will help make you more mindful of when you become distracted during work, school, or when you require yourself to be more focused. Use this guided meditation regularly to train the mind to be better at noticing distractions and bring its focus back to the present task. If you've enjoyed this, be sure to visit theclutterthemind.com for more.
All right, cool. All right. Let's do this.
Enough, it needs to be in the AN that is replacing may need to bubble up. We saw an example of that. It may need to bubble down. But interestingly enough, it needs to do only one of the two. Okay, it doesn't need to do both. So if I give it an opportunity to bubble up and it just stays in place, then I don't need to bubble down. I need to bubble down. If I give it an opportunity to bubble down, then I don't need to bubble up. So what I simply do is check the element in relation to its parents. If it's in the wrong relation to its parent, bubble up. Check it in relation to its children. If it's in the wrong relation to its children, bubble down. Both cannot happen. Okay, so this is an important thing for you to realize, that both cannot happen. You cannot have a situation where you both need to bubble up and bubble down. Okay, that will be a contradiction. And that's something for you to convince yourself. All right. So what's the complexity of deletion? Well, the complexity of deletion is very simple. It's one swap, two adjust size, and these are theta 1 operations, and three either bubble up or bubble down. In either case, and you don't do both, but in either case it's log n. So the complexity of deletion in a heap is just theta of log n. That's it. So it's also efficient deletion. So you can insert an element, you can delete an element very quickly. All right, very good. The next operation is to find the smallest element in the heap. So how do you find the smallest element in the heap? So if you're given a heap, where is the smallest element? We already showed in a min heap, this is going to be the very first element. Right? So finding the smallest element is very, very simple. Return a of 1. But be careful, I need to have a min heap. Suppose my application required me to find the largest element. I needed to have kept a max heap, okay, max heap, not a min heap, but a max heap. In a max heap, the very first element would be the largest element. In a min heap, the very first element would be a smallest element. All right. Okay, very good. Now, how do I find the largest element in a min heap? Well, unfortunately, it's not easy to find the largest element in a min heap. It can be anywhere in the last n by 2 elements, I guess. And so you need to do a search. Okay, so not all operations are supported in a heap. So if you have a min heap, then you're very efficient in finding the smallest element, but finding the largest element not so efficient. All right. Likewise, in a max heap, finding the largest element, you're very efficient. Finding the smallest element, not so efficient. Okay. So heaps are not sorted arrays. Remember that. All right. All right. So this is very good. All right. So this gives an application heaps. And this application is to a kind of queue called priority queue. And this is used all over the place, used in many places. Okay. And the important thing to note is this is super useful. And in fact, we will use it as part of other algorithms we will study in this class, which is why this is so important. So what's a priority queue? So what's a queue? So a queue is basically a data structure where you have people arriving. or this could be people. This could be processes, requests, whatever it is. And you store them in an array. And suppose you are able to, new request comes in. Request gets processed. So here you would insert, here you would delete, so on. Okay. Now this is easy, and one of the simplest kinds of queue is called a FIFO queue. First in, first out queue. Okay. But sometimes, and this is implemented everywhere. Okay, this is implemented in a lot of places. Most schedulers will implement it, and schedulers are used all over the place. Okay, so most schedulers will implement it. Packet switching, which is also a form of scheduling. So it's used all over the place. Okay, databases. This is used everywhere. All right, this is used everywhere. Now, one variant of the FIFO queue is that not everything is created equal. So some of them may be high priority, and some of them may be low priority, and some of them may be medium priority. So you may have priority levels for each task. Okay, so a new element comes in, it might come in with its own priority level, and you might have priority 1, highest priority, priority 10, lowest priority. You might have a priority number, and you want to process the highest priority ones first, and then the lowest priority ones last. You want to respect the priority. Again, this is super important in many applications. So in that case, what we can do is we can maintain a heap data structure. Specifically a min heap. If we maintain a min heap data data structure, okay, which is simply an array with some special properties. Every time a new element comes in, with the priority, let's say priority 8, I'm going to insert the element with the key equals 8 in this heap. Okay, so insert. And every time I am ready to process, I will always take the very first element because it has the lowest priority. It will always have the lowest priority. I will delete it and then restore the heap property by bubbling down in this case. All right. So this kind of a data structure is called a priority queue, and it's a very, very important application of heap data structures. All right. So new element comes in. Every time a new element comes in with the priority, let's say priority 8, I'm going to insert the element with the key equals 8 in this heap. Okay, so insert. And every time I am ready to process, I will always take the very first element because it has the lowest priority. It will always have the lowest priority. I will delete it and then restore the heap property by bubbling down in this case. All right. So this kind of a data structure is called a priority queue, and it's a very, very important application of heap data structures. All right. So the last application I would like to talk about is turning a given array. So suppose I have a random array. I would like to turn it into a heap. Okay, specifically min heap. But if I taught you how to do a min heap, hopefully you know how to do a max heap. Okay, so how do I turn an array into a heap? All right, let's think about this. So suppose I have any given array A. Okay, now how do I make it into a heap? All right, so this is an array of how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. All right, so if I wanted to draw it into a tree, even though it doesn't have the min heap property, I'm hoping to give it the min heap property later. All right, so the idea is really simple, and we will see why this idea works really well. So the idea is really simple. what we do is we are going to move from the very last element of the array to the beginning, move from end to beginning, and bubble down each element. So I will bubble down 9, bubble down 8, 7, 6, 5, 4, 3, 2, 1, bubble down. Okay, and in that process, what I will end up bubble array to the beginning, move from end to beginning, and bubble down each element. So I will bubble down 9, bubble down 8, 7, 6, 5, 4, 3, 2, 1, bubble down. Okay, and in that process, what I will end up with magically at the end is a heap. All right, let's do this. So if I bubble down 2, if I bubble down starting from the end, I bubble down, then nothing really happens for the first half of the last half of the array. Okay, so if I bubble down, bubble down, bubble down, so if the array is of size 9 or size n in general, then for elements from 1 to n by 2, they have children, but element from n by 2 plus 1 to n, okay, they do not have children. They are leaves. Why is that? Because remember, the left child of an element is twice that element, right? So if n by 2 plus 1's left child would be n plus 1 or more, and so it cannot have a child. Okay, so these elements from n by 2 to n cannot have a children. So for the first half of the array, bubble down is trivial. There's no work. In fact, I don't even need to do this. All right, and then let me come to 4. Okay, so then I bubble down 4. Does anything happen if I bubble down 4? No, because yes, it should, right? Because 4 is in the wrong relation with its children. If I wanted to do a min heap, then what will happen is 4 gets replaced by the smaller of its. By 2 plus 1 to n, okay, they do not have children. They are leaves. Why is that? Because remember, the left child of an element is twice that element, right? So if n by 2 plus 1's left child would be n plus 1 or more, and so it cannot have a child. Okay, so these elements from n by 2 to n cannot have a children. So for the first half of the array, bubble down is trivial. There's no work. In fact, I don't even need to do this. All right, and then let me come to 4. Okay, so then I bubble down 4. Does anything happen if I bubble down 4? No, because yes, it should, right? Because 4 is in the wrong relation with its children. If I wanted to do a min heap, then what will happen is 4 gets replaced by the smaller of its 2 children. So what will happen is 1 and 4 get swapped. Okay, so the new heap, let me draw the new heap, will become 2, 1, okay, 9, 15, let's leave this part, okay, 7, 6, and then 1, 4, and a 2. All right, very good. So now I have taken care of 4. Now let me bubble down 1. 1 is in the right relation with its children, so nothing happens if I bubble down 1. Let me bubble down 7. 7. Okay, so if I bubble down 7, what will happen is 7 gets replaced by one of its children. So in this case, 1 comes up here, 7 goes down here. Okay, and bubble down is recursive. So now I have taken care of 4. Now let me bubble down 1. 1. 1 is in the right relation with its children, so nothing happens if I bubble down 1. Let me bubble down 7. 7. Okay, so if I bubble down 7, what will happen is 7 gets replaced by one of its children. So in this case, 1 comes up here, 7 goes down here. Okay, and bubble down is recursive because 7 is still in the wrong relation with its children. It will get swapped with the smaller of its children, like that. Okay, so now 1 comes up here. All right, and finally, it's the chance of 2 to bubble down. So when 2 bubbles down, okay, so when 2 bubbles down, I will have it being replaced by the smaller of its 2 children. All right, and that's the final heap. So what's the idea here? The idea is really simple. Let me write down a for loop for I equals n by 2 down to 1. Okay, I don't even do the bubble down for the first n by 2. There's no need to do it. Bubble down a with I. And when I do this bubble down, then at the end of this, a is a heap. Specifically, in this case, the way we are doing it, a will become a min heap. Okay, and that's it. This is the heapify algorithm. Okay, what's the running time of heapify? Well, if you wanted to analyze it very simplistically, you could say each of these bubble downs can take up to log n time, and I'm doing it n by 2, so maybe it's n log n. Okay, is that the running time? Well, it is an upper bound on the running time. It is big O n log n. But if I wanted to get a better bound, I need to be more careful. So let me look at the array like this. So if I look at the heap, okay, at the very bottom of the heap, I have n by 2 leaves. Above that, I have at most n by 4 elements at the level above that. Above that, I have n by 8. Above that, I have n by 16. And I keep going until I have one element. So this is how a heap is organized. All right. Now, if I'm going to do bubble down here on these n by 4 elements, so if I do bubble down on this n by 2, these are 0 operations. So I don't even bother doing bubble down. If I do it on n by 4, these these are all one operations. If I do it on n by 8, these are 2 operations, n by 16, 3 operations, and so on. All right. So what's the overall complexity? So you see, not everything hits the worst case. The worst case for this n by 4 is just one operation, not log n. Right. So the worst case would be, let me write down the big summation. So it will be 1 times n by 4 plus 2 times n by 8 plus 3 times n by 16 all the way to log n times n by 2 to the power log n. So if you want it to be precise, then this would be summation j divided by n by 2 to the power j plus 1 for j going from 1 all the way to log n. Okay, and this is going to be an exercise for you later on. We can show that this is theta n. All right. So the overall complexity of Heapify is linear in the size of the array. That's it. Okay. Instead of n log n, it's simply n. It's proportional, directly proportional to the size of the array in a linear manner. Very If we have, okay, instead of n log n, it's simply n. It's proportional, directly proportional to the size of the array in a linear manner. Very good. Good. If we have all of this ready, then is we can actually use heaps for sorting to get a very interesting algorithm called heap sort. Now, what is heap? I would like to sort it in ascending manner. So the steps of heap sort are very simple. First, let me heapify the array, make the array into a heap. Okay, and then for I equals 1 to n, let me say the result, let me put the result in a new array, and let's call this the empty array. Okay, let's put the result in the empty array. All right, for I equals 1 to n, insert the smallest element into a of 1 into result. So what you're doing is, now that you have a heap, always take the very first element of the array and delete. And the very first element after you delete is still is going to be the minimum element of the array, and so at the end of this all, result will become the overall array sorted in ascending order, append into result. All right, so this is the easy version. Now the slightly more trickier version is, I don't want a new result array, so how do I deal with it without creating a new array? Because creating a new array means I have to double up the size of the data. Okay, very simple. Recall whenever I deleted, I took the very last element and I replaced it with the element I'm deleting, and I'm always deleting the first element. So why not reuse the space and simply move A1 back here. So what will happen is I can now use the deleted portion to store the sorted array. So I'll have the heap at the first part of the array, and the deleted portion, the portion that I'm growing as I delete each element, is going to now become the sorted part. Okay. Now the interesting thing is this will become sorted in the reverse order, in the descending order, and I can always reverse the array at the end to get an ascending order sort. Okay, not a big deal. What's the complexity? Very quickly, the complexity is going to be heapify is theta n. Each of these delete operations would be theta log n. So the complexity would be theta n log n. Okay. And you may object by saying that as I keep deleting, the size of the heap shrinks and becomes smaller and smaller. So this might not be theta log n, but the next step, this would be theta log n minus 1, n minus 2, and so on. But what you will find out that it doesn't make a difference in this case. It's still theta n log n. All right. So this is a very clever sorting algorithm that uses heaps. All right, so we have covered heaps. We have looked at heap operations, bubble up and bubble down in a bit of detail. And then we have, using those operations, we have shown how you can do heap sort and priority queues. All right, through insert, delete, and heapify operations. And that's the end of this series of lectures on heaps. Hopefully, you will be able to code up heaps and understand it. It's a very nice and very elegant data structure that's also extremely useful. Thank you.
Okay. So, select all the facts that are true about heap sort procedure in comparison with our search and merge sort. Merge sort. I need to go back here. Heap sort requires extra storage to store heap sort requires extra storage to store the heap, unlike insertion sort that can heap sort is asymptotically faster than merge sort. Yes. If an array is already sorted in ascending order. What? You're joking, dude. You're actually joking. Come on. Heap sort requires extra storage. I don't think so. Yes. If an array is already sorted in ascending order and the heap of hyper teacher is to run on it, then just not modify the array in any array. Ascending order? Come the depends if it's a min heap or a max heap. But okay, if a min heap is in fact already sorted in ascending order, yeah, deleting the minimum element operation runs in a constant time, sure. My thing is going crazy right now, bro. What is actually going on? 0%. I got this correct though. Okay. Let me see this. Incorrect, they are both sorting algorithms. Merge sort. Okay, merge sort. Sure. Okay, I'm tweaking.
blindness comes from. It actually comes from the most radical wing of the abolitionists. Since the 1960s, you have seen a process that began in the academy with critical race theory, and since 2013 or 14 has metastasized far more broadly on the left into elite left-wing institutions that has rewritten the history of colorblindness as if it's a bad faith idea coming from the worst corners of the far right. To the point where, as an experiment, right before I started writing this book, I just Googled colorblindness race because I wanted to see what would come up. 9 of the 10 links that came up were all articles arguing why colorblindness is bad, racist, reactionary, naive, etc. And the 10th was a Wikipedia page. So there's been a very successful PR campaign against the concept of colorblindness to the point where you've had celebrities that advocate for it have to walk it back and apologize publicly and so forth. And so my goal with this book is to tell the truth about the history of colorblindness, where it came from, to tell the logic behind the principle. Why is it such a good principle for a multiracial society? Why is it the only path forward? And that's really been my project for the past many months.
Modern people often ask themselves to read the field. Let me comment on that from a psychological and legal perspective. Okay, so I spent 20 years looking for markers, for psychological markers that would predict performance. Performance of managers, performance of students, performance of entrepreneurs, performance of creative people, and then on the negative side, predictors of antisocial behavior, criminality, proclivity to alcohol addiction, and so forth. Okay, and as part of that, it was very practical enterprise, because what I wanted to do was partly financially motivated and partly motivated by curiosity. I wanted to master the literature pertaining to the description of individuals so that they could be optimally fitted for their careers, let's say, or perhaps optimally diagnosed and understood if they were manifesting signs of the kinds of pathology that upset them and other people, typical clinical work. Now, there's quite a body of law around this. So imagine you're an employer and you want to screen your potential employees before you make them a job offer. Now, you should do that because you could make a case that you should just assign jobs randomly because that would be the most unbiased way of doing it, right? If you just accept all comers, there's no question about differentiation, discrimination, prejudice, anything like that. And so then you might say, well, why shouldn't you just hire people randomly? Well, there's a bunch of answers to that. First thing is that people actually differ in their abilities and their talents and their interests. And so it's in the interest of the person that you're hiring, as well as you, not to be mismatched to their job. Now, one of the ways you might match someone is by general cognitive ability. And you want people of higher general cognitive ability in jobs that require rapid learning and quick transformation, because otherwise they can't keep up. And then you might say, well, even if they can't keep up, it's not fair to deny them a job. And the proper response to that is, well, that means that someone else will be doing their job. And that's hardly fair to them. So, for example, if I hire a manager who has none of the attributes of a manager, all that means is he'll fail or she'll fail in that job, which is very painful for them. And it will also mean that they compromise the performance of not only everyone that works for them, but everyone that they're responsible to. And so there's just nothing in that that's good. You want to match the person to the job. Okay, so you can evaluate their temperament, you can evaluate their general cognitive ability. Those are the fastest and most efficient ways to make a determination of ability, merit. Okay, now, but the other thing that's interesting is that merit is actually described in employment law. So, for example, if I want to hire you for a position and I want to use a test to see if you're suitable, And by the way, an interview is such a test, and not a very good one, because interviews are not accurate. They're very inaccurate unless they're standardized and done by a group. So interviews are actually not without their prejudice. So what I have to do is I have to take the job and I have to describe what it consists of. And then I have to demonstrate that there's a statistical and I have to have an evaluation structure for those aspects of the job. So say it's quantitative. Then I have to show that my test is statistically associated with those outcomes. So merit in that case is defined as the ability to perform whatever the job happens to be. And then the acceptability of my screening technology is dependent on my ability to demonstrate a relationship between the technology and the outcome. So there's a bunch of reasons for making this clear, because what that means in a sense is that there's no difference between defining a job and defining the merit that goes along with it. Because what the merit is the ability to do the job. And so if there's a job, there's something that needs to be done. And if you're meritorious, you're better at doing it. Then the tests you use have to predict that. Now, there's no indication whatsoever that attributes such as race or ethnicity are relevant contributors to any job, not in and of themselves. So you can't screen on the basis of race, because race can't be demonstrated to be relevant to the outcome of the job. Now, the radicals say, for example, well, if you're black, you should have a black physician because only a black physician can understand your lived experience. And there's no measure for that. There's no demonstration whatsoever that that's the case. No one's ever demonstrated that, even a little bit. Certainly not in a way that a court would find acceptable and compelling if someone used that criteria for employment. The reason I'm pointing this out is because in some ways, the psychological and the legal communities had already addressed this issue. It's like you're actually legally mandated to be race blind. Now, unfortunately, the law is set up now essentially so that if you hire anyone, you're probably doing it illegally. You can be challenged no matter what you do. So I'll give you an example of that. So if I interviewed you and you didn't get the job, you could take me to court by claiming that an interview is not the most valid currently available means for assessing your suitability. And as far as I know, there haven't been court cases of that type, but they would, as far as I can tell, win, because the statistical evidence that unstructured interviews are unreliable and not valid is extremely strong. So the reason I'm bringing that up is because this issue of race blindness is, in some ways, it's already embedded in our legal and in our legal structures and our psychological practices. I can't evaluate you on the basis of race because it's irrelevant to your performance. So how do you understand the leftist objection to that?
Yeah, so you're exactly right. So many important features of the history get memory hold here. And the one that pertains directly to your point is the Civil Rights Act of 1964. This was the crowning achievement of the civil rights movement. It was fought over bitterly at Congress. I mean, most of the opponents at this time would have been Southern Democrats. This is, before the voting scenario and the geographical scenario in America rearranged itself. And this was as close to America has ever come to enshrining colorblindness in the law. What do I mean by that? What I mean is that when the Civil Rights Act of 1964 was being debated on the Senate floor, the lead sponsor of the bill famously said, if a single word of this act requires you to reverse discriminate or practice affirmative action to correct for imbalances, I will eat the entire bill page by page on the Senate floor. That's what the lead sponsor of the Civil Rights Act of 1964 said, Hubert Humphrey.
Mm-hmm.
Now, and now if you actually read the text of the bill, it's very clear. You just can't discriminate against anyone for any reason, and nothing in the bill requires you to reverse discriminate. So 2 + 2, that is a colorblind bill. Really, that's, you know, that's as colorblind as you're going to get. Now, how has it happened that in the 50, 60 years since then, that law has been interpreted by various judicial decisions to essentially require, to effectively require a kind of reverse discrimination in certain cases, right? The story of that is well told in Richard Hanania's book, and people can look to that if they want the details. But the intent of the Civil Rights Act was to be a colorblind, it was to enshrine colorblindness in employment law. And it ended up over the decades kind of pointing in a different direction. And that's one of the things that I think people memory hold, because the progressive left has now long abandoned colorblindness. And so it's an embarrassment to that fact that the entire civil rights movement was premised on it. So with respect to this, question of discrimination, this is a question I get quite often. People ask, Coleman, is it really that there are no situations in life in which it is valid to racially discriminate? And the way I answer that question is this. If you imagine an x-axis and a y-axis, imagine 4 quadrants. On the x-axis, you have stakes. Are you in a low stakes situation or a high stakes situation? A low stakes situation would be chatting with your friend at a coffee shop, right? A high stakes situation would be trying to find someone who on an airplane who you've just learned has a bomb, right? And now on the y-axis, you can picture information. How much information do you have, right? Do you have lots of information about someone because you've been, talking to them or hanging out with them for weeks? Or do you have no information about someone? Is this person a total stranger to you that you can only size up by sight? So if you picture that, 3 of those quadrants are situations where you really do not have a reason to racially discriminate ever, which is to say, if you have lots of information about someone, this goes to your point. If you know their psychological traits, if you've IQ tested them, if you've talked to them, if you've put them through a series of battery tests, if you've seen them under, all of that information is way more useful to you than knowing their race. Knowing their race adds no extra information because you've already got lots of information, right? So right there, that eliminates 2 quadrants. That eliminates both high information quadrants. Now, if you're in a situation where you don't know somebody, you're at a coffee shop meeting a friend of a friend for the first time, very low stakes, but you don't know anything about them, well then, rather than judge them on the basis of their race, the smart thing to do is just to get more information about them. And it's a low stakes situation, so you stand to lose nothing by doing that, right? Have a conversation with the person. In 10 minutes, you'll know more than you would know merely from a racial stereotype. Most of us live our lives in those 3 quadrants. And so there's not a good reason to racially discriminate. Now, if you are in the 4th quadrant, if you're in a situation that is high stakes, when there's lives on the line potentially, and all you know is that, say, there's a terrorist on this airplane who intends to blow up the airplane, well, then, yeah, it's valid to take race into account because you've got no time, and you can be pretty sure that the person with the bomb doesn't look like an old white woman, right? So I'm not saying there are no emergency situations in which you've got to, not be an idiot and pay attention to stereotypes and likelihoods and so forth. But the truth is, most of us are living our lives in the other three quadrants 99.9% of the time.
Remember when your personal life was actually personal?
I just want to hear what Jordan has to say about that, if he's going to comment on that.
And from a psychological perspective, from a statistical.
Jordan.
So, from a statistical perspective, and from a psychological perspective, the appropriate thing to do as a industrial organizational psychologist, for example, or a forensic psychologist, is to take an approach that's very much akin to the one that you just described. So the first thing is that people default to stereotypes when there isn't any other information. That's how we actually think. So when you don't know, you use a stereotype. Is it accurate? It's more accurate than nothing. Right, and that would be particularly the case in those high-stakes situations that you described. With regards to prediction, so I could imagine generating an equation to decide whether I was going to hire someone. Imagine I analyzed the performance of 200 people and I threw in general cognitive ability, past work history, and personality. That'd be a pretty good start. I might want to use some screeners of psychopathology. I could also throw in gender and race. Now, what I would want to do is see if gender and race, sex and race, I would want to see if they added anything above and beyond those additional, hypothetically more informative predictors. And the general answer to that, almost the invariant answer, is no. If you can control for factors that are more well-defined, and again, that's usually general cognitive ability and personality, then sex and race are irrelevant. It's not always the case, but it's virtually always the case. And so that means defaulting to sex or race makes your prediction worse. Now, people might also want to understand that we're also not only doing this prediction for the sake of the person who might be employed. So like, here's an example.
All right. So I went back and just sorted out the answers while I was watching that. Okay. I just want to review that for a second. So the worst case complexity, this makes sense. The procedure above is computationally less efficient than the one presented in class, this makes sense. Sorting. Achieve the same complexity, this makes sense because both algorithms have, the same complexity. Worst case of the procedure relies on that all makes sense. Okay, so I got this one right. Yeah, this all makes sense. I just got the other ones wrong when I clicked on it. If a min heap is in fact already sorted in ascending order, deleting the minimum element operation with the constant time. No, it'll always run in log. Okay, I get why this is wrong. Even though I'm like directed towards the answer though. Because I know it's wrong. So am I just, do I actually understand that it's wrong, or do I just already know that it's wrong? And I get why it's wrong now. That's the stuff you gotta be careful about, man.
Okay, so welcome to this lecture on hash tables. And in this lecture, we are going to describe a data structure called hash tables. Hash tables are going to be really, really important. They underlie many important data structures. For example, in Python, when you use a dictionary in Python, you are in fact using a kind of a hash table data structure. Okay, so what are hash tables then? So the basic functionality of a hash table is to implement mappings from what are known as keys to values. Okay, so we are going to be able to find if a key exists in a hash table. We are going to find out if we can insert a key in the hash table, we can delete a key, and we can also update the binding for a key. Okay, update the key value mapping. And these are all operations that are permitted by a hash table. And the goal is to do these operations effectively or efficiently, as efficiently as possible. So then what is the basic idea behind a hash table? Well, the basic idea behind a hash table is effectively or efficiently as efficiently as possible. So then what is the basic idea behind a hash table? Well, the basic idea behind a hash table is very simple. The hash table is a table. And so you have rows of your table, and these rows are variously called slots or buckets. Uh, okay, buckets or slots. So you have various names for these, and or bins, right? Uh, but remember, they are just referring to the rows of a hash table. All right. In this case, your hash table has 7 rows, indexed from 0 to 6. All right. And you have each row, you have a key and you have the corresponding value. All right. So you have keys like John, Sarah, and Mabel, and the value that John is associated with, the value that Sarah is associated with, and the value that Mabel is associated with. In this hash table, the keys are of type string, and the values are of type tuple, of an integer, floating point number, string, and a floating point number. All right, so this is the how the hash table is designed, and the design doesn't matter if what the type of your key is or what the type of the value is. What matters in a hash table is a very special function called the hash function, and that's the hash part of the hash table. So the idea behind a hash function is that it takes in a key, in this case John, and somehow it computes a number. For example, J can be mapped to 11, O to 15, H to 9, N to 14, sums it up modulo 7. Why modulo 7? Because I want the result to be a number between 0 and 6. Okay, and in this case, I get 49 modulo 7, which is 0. So therefore, what the hash function dictates is that if John function called the is doesn't it doesn't matter if what the type of your key is or what the type of the value is. What matters in a hash table is a very special function called the hash function, and that's the hash part of the hash table. So the idea behind a hash function is that it takes in a key, in this case John, and somehow it computes a number. For example, J can be mapped to 11, O to 15, H to 9, N to 14, sums it up modulo 7. Why modulo 7? Because I want the result to be a number between 0 and 6. Okay, and in this case, I get 49 modulo 7, which is 0. So therefore, what the hash function dictates, is that if John were to appear, John would appear only at this slot 0. So the slot 0 is the only slot in which John would appear, at least in the initial design. Let's keep it that way. For example, here is another key called Joseph, and you apply the hash function to that key, you get the summation, and let's say you have the slot 5. So if Joseph were to appear, Joseph would appear in the hash table in slot 5. So that's the key idea behind hash table. And the operations that are supported include find, if a key is in the hash table. Okay, if it is, then return the corresponding value, otherwise say no. So for example, if I were to find John, then I would hash John, that would give me 0. I would look up slot 0. Sure enough, there is John in slot 0. There's the key John. In slot 0, and I would return yes, I found the key John with this value. On the other hand, if I were to find if Joseph were in the hash table, I would again hash it. I would find the value 5 for the hash function, and I would go look into slot 5. And in slot 5, there is nothing. There is currently nothing in slot 5. So if you ask me to find Joseph, I would say, no, Joseph is not in the hash table. Likewise, we can insert a key with a value or delete a key with a value from a hash table. Now, the key idea behind the hash table, therefore, is that there is a hash function that can be computed efficiently. So the hash can be computed quite efficiently. Typically, we assume it takes like constant number of operations to compute the hash function, all right? Even though that assumption is not always true. For example, the size of the string matters, but we are not going to take that into account here. All right, so we'll assume that the hash function is computed effectively, and it tells us where to look if we wanted to find a value with that key. That's the key idea behind a hash table. So then what is a hash function? Well, a hash function is generically any function that takes a key to a slot in the hash table or index of a slot in a hash table. And the key thing is it must map the key to the slot in the hash table. So hash of key in this instance must be a value between 0 to 6. You can't have 7 or 8 because they are not valid slots in the hash table. So the hash function goes along with the table. So it goes along with the table. All right. Now, one of the issues with the hash function is it needs to map a lot of keys, and it may be possible that some other key maps to a slot that's already taken. So, for example, you may have like hash of someone called Periwinkle, uh, could be like 0, which means that Periwinkle, if they were to be found, if that key were to be found, would be found at slot 0, but there is John at slot 0. All right. So the hash table, unfortunately, the hash function is not unique. So it can map a lot of keys to the same slot in the hash table, to the same slot in the hash table. And we have to deal with that. That's the price we pay for this. And the question is, how do we deal with that? But before we deal with that, let me spell out how does insertion work in a hash table. Well, the way insertion works in a hash table is suppose you're interested in inserting Joseph with some value. Well, you compute the hash function. So first step, compute the hash function. It tells you if Joseph were to be inserted, where would Joseph be inserted? Let's look up position 5. Honestly, it's empty here, so no problem, right? So you insert Joseph and you insert the whatever you were asked to insert as the value. All right. And that's it. So insert is quite simple. You just compute the hash of your key, look up that slot. If it's empty, then insert is simple. On the other hand, suppose you just inserted Joseph and now someone wants you to insert Simon with some value, but the hash function of Simon is also 5. But on the other hand, you already have Joseph with this value at 5. So this is a situation which you have to deal with, and this is called a collision or a hash collision because the keys Simon and Joseph collide. They collide to the same slot in the hash table. So then different hash table data structures differ on how do they handle a collision. So how do they handle a collision is the main thing that we need to look into. All right. Uh, how do you handle collision? Well, the simplest idea and the first idea we will look at right now is called chaining. So, and what is chaining? Chaining is a very simple idea. Instead of your hash table being like in the previous slide where you have a key and a value in a single row, instead make your hash table slightly different. Each slot maps to a list, initially empty, initially empty. So initially the list is empty, but the list can grow and contain multiple key value pairs. And that's the basic idea behind chaining. So in chaining, each slot is associated with a list of key value pairs, and the list can grow dynamically. Very simple idea, the main thing that we need to look into. All right. Uh, how do you handle collision? Well, the simplest idea and the first idea we will look at right now is called chaining. So, and what is chaining? Chaining is a very simple idea. Instead of your hash table being like in the previous slide where you have a key and a value in a single row, instead make your hash table slightly different. Each slot maps to a list, initially empty, initially empty. So initially the list is empty, but the list can grow and contain multiple key value pairs. And that's the basic idea behind chaining. So in chaining, each slot is associated with a list of key value pairs, and the list can grow dynamically. Okay. And that's the key idea behind behind chaining. There's nothing else to chaining other than that. But then how does insert and all those things work? Well, how does insert work? Well, insert works like this. Suppose I wanted to insert a key and a value. You look at hash of key as before. So let's say it hashes here to slot 3. Suppose it hashes to slot 3, then let me just append this key value, assuming that it's not already there in the hash table. Let me just append it to the end of the list. If it is already there, if you think it's already there, you may want to search each of these keys and see if any of those keys matches the key that you want to insert. And if it does, then simply update the value. So these are things where you can handle them if you don't want multiple keys to map to the same value. The same key to map to multiple values. If you do not want the same key to have multiple values, then you simply will have to check that the key is not already present. And that's also the algorithm for find, right? Which is also very simple. If you want to find a key, first hash the key. That tells you where to look, and then search the linked list one by one, or search this list one by one to find out if the key is available. So find and insert are easy. How about delete? Delete is also like very easy, right? So if you want to delete a key from a hash table, let's say you want to delete key 2. From a hash table, let's say you want to delete key 2. I first do hash key 2 just to find out if key 2 were there, where would it be? And in this case, it better return 0 because we secretly know here it is. Well, once it returns 0, search through this list. And once you get to the second element, it matches, delete the second element from the list, as simple as that. Okay. And we assume that there is a list data structure like in Python. Okay. And the list data structure or the dynamic array data structure can be used in this instance. All right. This is good, but it comes at a cost. And what is the cost? The cost is, in the worst case, suppose I have a hash table in which I insert n elements. In the worst case, all those n elements can just go to the same slot. Because why? Because our hash function may be a poorly designed hash function. So someone just gave you a dummy hash function that always gives you the same answer. Or your worst enemy chose those keys very cleverly so that knowing your hash function, they all went to the same slot. And this is called adversarially chosen keys. Okay. So in that case, every operation, in the worst case, every operation will need to search through this entire list. And therefore, the worst case complexity of insert, find, and delete are all order n. Okay, order n, which is you have to search through every element in the list. Now, you can talk about something called an average case, even though in this instance, it's not a very well justified average case. We will revisit this when we talk about universal hash functions, okay, or random hash families. So we'll have to revisit this issue. But a naive way to think about it is, suppose somehow I have managed to distribute my keys on the average. So somehow these assumptions don't hold, and somehow the keys have been distributed as if they are being distributed randomly. All right. So then what you can say is any particular key k sub I will hash to the slot j with probability 1 by m, where m is the number of slots in the hash table. Okay. So therefore, in this situation, you can actually prove that the average size of each list is n by m. What is n? N is the number of elements, and m is the number of slots. This makes perfect sense, right? If you have a hash table with 100 slots and you randomly put in 200 elements, then you would expect 200 divided by 100, which is on the average, if things were well distributed by this assumption, you would expect each linked list to have about 2 elements, So the average case complexity then of each list is n by m. Okay, so the average case complexity of insert, find, and delete is this thing called n by m, and this has a name. It's called the load factor. So what is the load factor? Load factor of a hash table is the number of elements that have been inserted into the table by divided by the number of slots. So with probability 1 with a random hash search that are list each and being your hash there and which is you have to search through every element in the list. Now, you can talk about something called an average case, even though in this instance, it's not a very well justified average case. We will revisit this when we talk about universal hash functions, okay, or random hash families. So we'll have to revisit this issue. But a naive way to think about it is suppose somehow I have managed to distribute my keys on the average. So somehow these assumptions don't hold, and somehow the keys have been distributed as if they are being distributed randomly. All right. So then what you can say is any particular key k sub I will hash to the slot j with probability 1 by m, where m is the number of slots in the hash table. Okay. So therefore, in this situation, you can actually prove that the average size of each list is n by m. What is n? N is the number of elements and m is the number of slots. This makes perfect sense, right? If you have a hash table with 100 slots and you randomly put in 200 elements, then you would expect 200 divided by 100, which is on the average, if things were well distributed by this assumption, you would expect each linked list to have about two elements, So the average case complexity then of each list is n by m. Okay, so the average case complexity of insert, find, and delete is this thing called n by m, and this has a name. It's called the load factor. So what is the load factor? Load factor of a hash table is the number of elements that have been inserted into the table divided by the number of slots in the table. So on the average, we expect the complexity of insert, delete, and find to be the load factor, but not yet. We can't expect it right now. We'll have to show a very cleverly designed hash function scheme to get that. Okay, but right now I'm just introducing the concept of a load factor, because in many hash table implementations, load factor comes in key. So what happens is, initially you start with a hash table, let's say of size m. Let's say initially you start with m equals 16, and you track the load factor. So you track the number of elements n. And usually when n, let's say, is greater than or equal to 8, when the load factor is greater than or equal to half, which means your number of elements exceeds half the capacity of your hash table, then you move from this to a new hash table, okay, of size 2m, and you take each existing key and value and hash it according to this new hash function, okay? Introducing the concept of a load factor, because in many hash table implementations, load factor comes in key. So what happens is, initially you start with a hash table, let's say of size m. Let's say initially you start with m equals 16, and you track the load factor. So you track the number of elements n. And usually when n, let's say, is greater than or equal to 8, when the load factor is greater than or equal to half, which means your number of elements exceeds half the capacity of your hash table, then you move from this to a new hash table, okay, of size 2m, and you take each existing key and value and hash it according to this new hash function, okay? And this operation is called rehashing, and the complexity of rehashing is order n, which is the number of elements, because you have to go through every slot in this hash table, and you have to take each element and rehash. So in fact, since you have to go through every slot, it's actually, if you want to be more precise, it's n plus m, because you go through each slot and you go through each element in each slot. So there are a total of n elements, and you have to go through each slot, because many of the slots could be empty. And if they are empty, then you still have to go through them and check that they are empty. So it's n plus m, and you move to a hash table of size 2m using this new hash function, okay? And you expect the complexity to be order n of inserting into a new slot each element, and you, let's say, you insert at the head of the list, so you don't have to go all the way to the tail or something like that. So it's order n plus m is the cost of rehashing, and that's frequently done to manage the distribution of elements in the hash table, so you don't get too long chains of elements. Okay, so some concluding thoughts on hash tables. We have just introduced this very fascinating data structure, and we have talked about chaining, okay? But we need to talk more about hash tables. In particular, we'll talk about hash function families, okay, to actually get really good randomized guarantees for hash tables. We'll talk about hash function families, and we'll talk about some other ways, other alternatives to chaining. Okay, including some very clever alternatives like open address hashing. We'll talk about that, and something called cuckoo hashing. We'll talk about that. Okay, So hash functions tend to be a very, very useful data structure in computer science. And it's one of those data structures where it's very useful to know more about hash functions and how they work, because a lot of interesting algorithms can be designed using these hash tables. So I'll stop there. Thank you, and see you in the next lecture. By 2, there's no need to do by saying. And that's the end of this series of lectures on heaps. Hopefully you will be able to
I'll take a break and I'll be back.